So it's a pleasure to get a chance to report to you guys some of the work we've done recently about black hole quantum modes, spectral instability, etc. So just before start, so feel free, absolutely free to interrupt me just anytime. And I'm going to talk about mostly based on a recent study on the Greybody factor and the Regge pose. But also, as the motivation for this study, I gotta go through some of the works we've done also in collaboration with these guys about black hole spectral instability and some related issues. So it's essentially it's going to talk about an interplay about several concepts. So like start with spectral instability, asymptotic modes, and the instability in the quasinormal mode, both for high overtones and the low-lying modes, and their connection with gravitational wave echoes, and also there's a paper recently about reflectionist mode and Regge pose, and the observational implications about if this spectral instability might impact the ongoing black hole spectroscopy. So this is more or less the outline of this talk. So I think everyone is expert in this area. So I just pick out some of the points that is more relevant to me. So I think first, quantum mode is a classical concept. So we don't really need a quantum theory to discuss a quantum mode, which corresponds to the resonance states, which has a non-vanishing imaginary pattern frequency. Also, we don't need the curved space-time to have quantum modes. Essentially, it happens for open non-Hermitian system. And so most of the discussions will consider this simplified case. It's a one-dimensional radial mass equation with an effective potential. The simplest one is the Regge potential. So for a big part of this discussion, so we're going to view this the solution of quasinormal modes as the scattering, classical scattering problem with this outgoing wave under conditions. And so this is an incomplete list of approaches, which is essentially involved for the analytic and the semi-analytic approaches for the quasinormal modes. To discuss the spectral instability, we will be more focused, for instance, for the symptotic modes. So then the list becomes smaller because we need to concentrate on either we can derive the symptotic modes analytically or consider certain entirely analytic scenario. So this actually limit the means that people can employ for these studies. If we use numerical studies, so it's up to the algorithm we employ, but usually the overtone number is relatively limited. So the entire notion of spectral instability starts from Knowledge's paper. So that was almost 30 years ago. Then that he considered approximation of the Regge effective potential by piecewise staircase approximation. Then he showed that the tendency of the modes which goes along the real axis of the frequency instead of climb up along the imaginary axis. So this is quite well known and was left for a while. Then Ramin and Michael and Jordan, they published a paper 3-4 years ago. So they they refine some of the approximation and try to see if it's not because of the particular feature of the approximation which was employed back then, but still they find essentially the same conclusion. Then inspired by this, that was 1 year later. So we look at this problem saying maybe we just introduce a small step, and by the end of the day we introduce a minor discontinuity, which is not even in the effective potential. It can be in the high order derivative of the effective potential, but for the black hole metric, which is simplified enough, we can try to derive the property of symptotic modes, and we show that this behavior persists. I think this is also recognized by this paper, where some of the authors is here, but they performed a more systematic analysis and used the term, I think it was structural instability, but I think today more people refer to it as spectral instability. So I think from a more general perspective, so it is shown that this kind of instability is more easily triggered if you introduce, they call it ultraviolet metric perturbations. To my understanding, these are the perturbations with small spatial scale, and the magnitude of perturbation can be really small, but the wavelength, the frequency should be big enough so that this is, I think, for the Oshita, for the Oshita. So introduce a very small amount of perturbation, then the spectrum is deformed entirely close to the bound, which is accessed from a different approach. So I think this is the seminal paper that lead to the topic that we followed. Then the feature which I sort of summarized, but more from the point of view of our papers is first, definitely it's a stability of the entire spectrum. It's not for individual states, so it's a different notion of quasinormal modes. So all the states, they remain stable, but the form of the spectrum become very different. So this is a different thing, as in quantum mechanics, we have perturbation theory, but in that case, the Hamiltonian is Hermitian. So this is, people usually attribute the difference to this mathematical sort of property of the Hamiltonian of the system. And as a matter of fact, no matter how weak the perturbation is, it leads to drastic modifications. At least in the paper, the focus was on higher electrons. So essentially the idea was the fundamental mode and the lower electrons, they mostly stay unchanged. As a result, that the temporal waveform also mostly remain unchanged, but those high overtones are drastically deformed. So this is more or less the notion that I summarized. Then I would like to mention a couple of studies which are related, and it is related to study. So the first is the gravitational wave echoes. It was first proposed by Cardozo and his collaborators. It was introduced as I think partly as a sort of observable to probe the property of the space-time near the horizon, to differentiate some of the black hole mimickers, at least to my understanding. But if you look at the the analytical property of the green function for these echoes. So one way to introduce echoes is instead of you perturb the metric near the horizon, you can actually also introduce a small perturbation far away from the compact object. And numerically, this is shown on the right panel. This is you also effectively generate some gravitational wave echoes. And actually for both cases, if you look at the symptotic behavior of the poles of the green function, so they display essentially the same property as the PIX paper proposed and referred to as spectral instability. So we understand that they are on this level in terms of the property of the poles of the green function, they are very similar. So this is one point. But this is more about symptotic modes, they're about high overtone. Then there's this another paper which is also has a bigger impact recently. It's about the fundamental mode. So these also show that the fundamental mode is also unstable and this in spiral that grows outside exponentially, and the size is big enough if we consider the corresponding temporal waveform and consider size in the frequency complex plane. It might have observational implications. Then it is triggered also by a very small ultraviolet metric perturbation. And this spiral happens when the perturbation moves away from the compact object. Right? So to assess this, immediately there are several papers. And I think in 2 years following that, but to our knowledge, so most of the studies, they considered two disjoint potential barrier. So one is resembles the background black hole metric. The other corresponds to the perturbation. So the other potential barrier is much smaller. So comparing, so they consider this problem effectively as a scattering problem. You can calculate the quasinormal modes considering the potential vanishing between them. So you can use the scattering amplitude of the scattering matrix to evaluate the deviation, the impact to the quasinormal. And this was shown by actually simultaneously, I think independently by various sources. And it was for us, because our paper come later after that, maybe a couple months later, but the calculation was done much earlier because we delayed, we didn't expect. But we point out something a little bit different, is if you do not consider that the metric perturbation is entirely separated from black hole metric, you may lead to different conclusion. For instance, if you introduce a small perturbation for the post-Taylor potential, so we can actually show that the fundamental mode is stable. This can be done analytically because we have access to mostly analytical form for the symptotic wave functions. So we can carry out this calculation, carefully expand this and do the analysis. So there's a difference there. So if you put the metric perturbation on top of the background metric, it's not always lead to the conclusion that the fundamental mode is unstable. If you have two potential barrier, they're separated, then it's independent of the specific form of those potential barriers. It will always be unstable. But if you consider, in that sense, more maybe physically pertinent scenarios and look into those details, we may lead to some different conclusion. But anyways, for the Ridge-Wheeler potential, it remains unstable, even though the perturbation is right on top of the effective potential. And also we have a study regarding a dynamical picture of this. I should go a little bit faster. Then there was a paper by Licia, and that was also a while ago. They considered perturbed Pochsteller potential. And back then, I think people don't really have this notion of spectral instability. So the calculation was based on the assumption that the quasinormal modes will only be perturbed little bit. And based on that, they carry out the perturbation and the result was consistent. They didn't perform any numerical calculations. Everything is analytic. So this leads to a kind of question mark to us is we know if you perturb Pochsteller effect potential, you have spectral instability. Then there was an old paper saying it is just mildly perturbed. So is there any contradiction between those conclusions? So we did a calculation, both numerically and analytically. We show that, so let me explain the perturbation involved in this. So VC and his co-author, they introduced a perturbation at the origin of at the maximum of the effective potential, and evaluate he just mismatch two sides of the Pochsteller potential. So effectively, you have something discontinuous, and this difference is very small. And they calculate the quasinormal modes. So their calculation is analytic. This is shown here by the empty blue square. So this here. So we calculate a numerical calculation and a semi-analytical one, but the calculation performed to, if we call this calculation first order, so we go to like 1.5 order. We consider some other terms, but not really went to the high order. So these are shown in by this solid red circle and the triangles. So if you look at the bigger scale, everything matches. If you look closely, so it shows, of course, everything is consistent, but we do capture some small deviation on top of the approximation that VC did. But in conclusion is everything is consistent if you introduce a small perturbation near the maximum of the Pochsteller effective potential. So this is this plot. However, we know as following as the studies, you can move this perturbation away from your compact object, from the maximum of the Pochsteller potential. And this is shown here. So just to show everything is consistent. So this plot is essentially the same. Showed previously, except the deviation is small. If we look from this scale, we don't really see. But if we move the perturbation away from the black hole, we can see that they start to deviate, and eventually there's a bifurcation, and both sides they fall right on the imaginary axis and form these purely imaginary modes. We know that there's a numerical artifact sometimes to get imaginary modes, so we also derived them semi-analytically, showing they are the real modes. Then this branch goes along the real axis, so it corresponds to the spectral instability. As further move away, we can see this instability propagates towards the low overtones. So this is just a plot that we show that the fundamental mode of Oshita potential is actually stable. It spirals in. This is we did the numerical ones and analytical ones, and they match. Then go to the topic. So so the question here is whether these things had observational implications. So that was last year. So both groups by Rosato and his co-authors or Oshita and co-authors, I think they released this almost simultaneously, saying that Greybody factor is sorry for the typo. Greybody factor are stable observables. So these are the plots from their paper. So we can it's difficult to see, but they are all together for the perturbed and unperturbed black hole metric, Regge effective potential. So at least for this region, that you don't see sizable or visible difference between the Greybody factor. And if you go to really high frequency, this is pointed out by Oshita's paper, that it matches the WKB approximation. So it oscillates, but it symptotically approaches this. And regarding the studies, there's a different thought is so Greybody factors that essentially related to the scattering amplitude. And quasinormal modes can be understood as the poles of particular scattering amplitudes. And the Greybody factor is only evaluated on the real frequency axis, and quasinormal modes is on the complex plane. So maybe I pose a naive question. So the insensibility, which is shown by the Greybody factor, which is on the real frequency axis, maybe because the poles are in the complex plane. So the small deviation on the complex plane doesn't significantly impact the quantity when it is evaluated on the real axis. So this stability maybe just that. What? So I don't actually to my best knowledge, I don't see other people asking this, but it was a question to me. So why what is the real argument? And also the for the black hole spectrum, spectral scope. So the purpose is to extract the underlying black hole metric parameters from the gravitational waves. So if this observable Greybody factor is stay the same, what's its impact on this process to extract the underlying parameters? I do not see a direct answer to this if we just look at the Greybody factor, right? So this is essentially the motivation of what we did. And honestly, I don't think we fully answer this, but maybe finish some answer pathway to this. So first argument regarding this is we can view the Greybody factor both. First is they are, because of the quasinormal modes, they are the poles of the scattering amplitude in the complex frequency complex plane. But also, Greybody factor, since it's directly related to the scattering amplitude, etc., etc. So there's another way to see this. So it receives contribution from different partial waves in terms of partial waves of different angular momentum. And there's this Regge poles. So in terms of Regge poles, we can also express the Greybody factor in terms as a summation of contribution from different complex angular momentums. So we do the analytic continuation this time, not for frequency, but for the angular momentum. So these two views, as pointed out by, sorry I didn't put the paper there, but by some authors, is you are just looking at the same thing from this different perspective. So regarding these two different approaches, so which one is more relevant? I will say the following. If there is no spectral instability in the ridge poles, but you do have spectral instability in the quasinormal modes, and for both cases, high overtones, they climb up around the imaginary axis of frequency of angular momentum. This, we already know that. But if there's no spectral instability in the ridge poles, then definitely the conversion in terms of ridge poles will be much better. So they do furnish a more stable observable when you expand things in terms of ridge poles because they're stable.
Hey, Wei-Liang, can I ask you
Sure.
or make a comment here?
Sure.
There is a paper by Leo Torres where he
Yeah,
shows that
I'm going to talk about this.
okay,
Right.
great,
Next
because
slide.
okay,
Yeah,
cool,
because the
the ridge
answer
poles they
is
have
no.
okay, yes.
Right. So this paper, right?
Yes,
So
precisely,
actually
yes.
he showed the instability in ridge poles. So this doesn't, like, it's a speculation, but it doesn't help. And however, there's one conclusion in his PRL paper, which is also interesting, is he calculated this. This is a differential scattering amplitude. And he summed up the ridge poles. And he does show that if you take into account the contribution from, you do need to sum up until 15 ridge poles, but when you sum up those things, you do recuperate pretty well the differential scattering amplitude. This is kind of in contradiction of what he is showing in the very same paper, that there's a spectral instability right here. So in the next, I don't have a lot of slides. I'm finishing, but is trying to reflect on these seemingly difficult, like to converge the result. They don't seemingly converge just by themselves. So why? Then I have to show this because we use this hyperboloidal coordinates to do the calculations, and we implement it to a approach we call it matrix method. We usually do both. You try to do both the numerical and analytical to make sure we did things right. And for the numerical ones, we were using this for the most of the implementations coding, using the hyperboloidal coordinates and implement it to the matrix method. There are two things. First is this instability of ridge poles. They do occur in the ultraviolet region. They actually happens when the frequency is big. If you consider small frequency, the spectrum is essentially stable. In Torres' paper, that there's only one plot, but you can do the same calculation for different frequencies. And this is show clearly that it happens mostly at high frequency. And this plot on the screen is showing if you move this, we consider the metro perturbation as a discontinuity. So if you move it away from the compact object, and the instability also increases. But let me go back. At low frequency, there's not that much spectral instability. And this is the regime that we need to take into account a relatively large number of ridge poles, as shown by there's a plot that by first did by Torres, that he sum up until 16 or 15 ridge poles to get a convergent result to the numerical calculations. However, that plot he calculated is actually for low frequency. And this is the region you don't have the spectral instability, so you do have the freedom to sum up enough ridge poles and without worrying about the spectral instability. On the other hand, at high frequency, this is where that the spectral instability become a problem. However, at really, really high frequency, at really high energy, this is the regime where we can look at if this is electromagnetic perturbations. So this is when the radiations become light rays. So that is the region where the Eckernal limit serves very well. So in that region, the contribution from the partial wave actually become less important. You can just look at the lowest, at the background, that is the Eckernal limit, which is actually the sort of residue of this contour integration. Then we sum up the contribution from the ridge poles. But numerically, we can show that just adding the first, second pole, you get very good result. So we have a plot for this, I think. Yeah, so this is a comparison. If you at high, this is high frequency, you have consider just one pole or you consider 8 poles, you are perfectly fine. You reproduce this sigma cross section pretty well. So in the region where spectrum instability become a problem, we actually have this semi-classical high energy limit works for us that we don't need to worry about spectrability. And in the low frequency region where spectrability is not a problem, we do need the contribution from the ridge poles, but then it's also okay because there's not much of an issue due to the stability of the system. So this is essentially that we point out in the paper. So this is a conclusion remarks. I think this is the most of the things I want to say. Thanks a lot.